In this video, we will look at solving integrals via U substitution when they are definite. And the short answer to how is it different when it's a definite integral is that it's the same, you just need to also change your boundaries. Because another thing to remember about boundaries of integration is this corresponds to area under the curve. So we could imagine this as a graph of some sort of function that looks like whatever it does. And if we're taking a definite integral from 2 to 5, that's going to give us the area underneath the curve on the x-axis from 2 to 5. So it's important to remember that those values are coded to be x values, and they match the variable that is in your differential, always as an assumption. In order to evaluate it, they have to be matching. And the same goes for the variable within your integral. If you're going to apply rules of anti-differentiation, all of those have to be the same. Those are all x values. So if we're going to change things to u, then we must change everything to u, including those boundaries of integration. But to begin with, don't worry about that. Just start with the same exact process from before. And actually, the first integral is one we just solved a moment ago in the previous video. We already know the general antiderivative. But in the same way, when we have 1 divided by something, often setting the denominator equal to u can help us solve that. And that would leave us with du is equal to 2 dx. And again, in converting this, since I don't have a 2, I could divide both sides by 2 and say, well, du divided by 2 is equal to dx. And perform this substitution. So again, kind of looking at this, we'll have 1 divided by 2x plus 3, and that's what I chose to be u. And dx I solved then to be equal to du divided by 2. Or again, I could write that 1/2 directly out front, which is fine as a shortcut, because this is du over 2. That's the same as 1/2 du. And 1/2 can be pulled through the integral symbol. Now, though, what about the boundaries? If I just leave these as 2 and 5, that's all going to be wrong. Because basically, when you're changing your function from this to this, it's actually changing the graph. And the area underneath the curve is going to be correspondent to a different interval because it's with respect to u now. So these values in the integrand, or the boundaries of integration, also need to be in terms of u, not x. And if you're wondering, well, how do I do that? Basically, just like we did here, we need to use our u substitution relationship to do that. And so what I like to do is write, well, x started at 2 and 5. And then I want to know what are those with respect to u. And from here, let me actually give myself a little more space. I can use the original u substitution. That's how you need to change your values, because these are x values, and if I want to change them to u, I just plug them in, because u in this example is just a linear relationship. U is equal to twice x plus 3. So, well, if I just plug that in, x is 2, 2 times 2 is 4, plus 3 is 7. So if u is 2, that means u would have to be 7. And for 5, well, I get 2 times 5, 10 plus 3 is 13. And so I would change those boundaries of integration based on that linear relationship, and my boundaries will now change from 7 to 13. Technically, you can write that these are x values and u values to specify, but that's always implied in an integral if you're not writing specific parameters. So notice that most of the time people don't write what variable is within the boundaries of integration because that's extra writing. But that just keep that in the back of your mind, is that this needs to match this and those values. If you're changing your integral, you also need to change your substitution. Now that all said and done, I can, again, now it's just a definite integral in terms of u, and I would solve this as I would normally do. So now that everything has been changed to u, I can solve this problem. Well, the antiderivative of 1 over u, as we already know, is the natural log of u. Again, I don't need c here because it's a definite integral, and I just would need to evaluate this integral from 7 to 13. And then plugging that in, that just means, well, the natural log of 13 minus the natural log of 7. Remember that 1/2 will be multiplied to the whole thing, because 1/2 is multiplied to the whole integral, both the first and the second boundaries of integration. And the rule for natural logs is actually, well, the natural log of 13 minus the natural log of 7 is just amounts to the natural log of 13 divided by 7. That's log law number 2, as a lot of people call it. But anyways, again, we could always use a calculator or whatever to simplify from there. But that's, definitely a good enough answer, or we could get that as, since that's corresponding to area under the curve, we could actually solve, well, what is that in square units as well. And actually, before we do another example, I wanted to mention what's another way that some people do this. And actually, you can do all of this without changing the boundaries as well. It's a totally different procedure, but it's almost exactly the same. And some of my students occasionally prefer this way of doing it, or they've been taught to do it this way before in some other context. So it's totally up to you. As always, you can solve things however you want to. I always like to show you more than one way to do things in case a different method resonates well with you. But basically, going back to the step where we perform the u substitution, and we change the inside to 1 over u and the du here, you don't even actually need to change x to u. You could just leave them as x values. But notice that what I'm going to do is I'm going to leave it as x is equal to 2 to 5, as it was with the original integral. So I do need to change the, I need to change u, and I need to change dx to du properly, as we did earlier. But basically, if you want to skip this step, you can. But you have to mark that those are x values. Because if you don't, again, the implication is that those are u values, and if I'm not changing them, notice how I could leave them and write x in there. Now I could solve the antiderivative, and I would get the natural log of u. And again, I could say, well, from x is equal to 2 and x equal to 5. And again, this would let me alert myself to notice, okay, I can't plug those in because that's not a matching variable. Now I could reverse the substitution as we were doing in the last few videos, as we normally have to do when we're dealing with x, because u is just equal to 2x plus 3. And now that I resubstitute back in x, now these boundaries of integration match the x, and I could drop the x equals from my notation. And now I could just plug those in. But what you'll notice as well, if I plug in 5 at the end of the day, I will get the natural log of, well, 2 times 5 plus 3 is 13, and 2 times 2 is plus 3 is 7. And I'm going to get the same answer. I personally think it's much simpler to change the boundaries than do all that. But, this is basically, it's the same exact procedure as we did before. You just have your boundaries of integration, and you wait till you solve your antiderivative to plug them in. So, if that makes more sense to you, that's cool too. Let's do one more example before we wrap up this week's lecture. So again, looking at this one, I would start by setting the interior as u, because if I notice I have x squared, the derivative will be 2x, and that's close to 3x. So before I start doing anything, I would look at it for a moment to think about, if I'm going to do a u sub, what do I think might be the best choice? And then du would be 2x dx. Here, though, notice I have 3x, not 2x. So what I could do is just divide by 2. That would just solve for x dx. And then this 3 I could kind of ignore or pass through the integram. So I could kind of go like that if I wanted to. Now I have x dx is d over 2 based on this equivalency. So x dx is right there, and there would be d over 2. And then u is just going to be what I had on the inside, which is x squared plus 1. Oops, sorry, that's a little bit crazy looking. And that's just going to be the square root of u on the inside. And I had the 3 that I pulled out front. And again, like how I like to do it is I like to change the boundaries just so my whole integral is in terms of u. And if you do this, then you don't have to resub. It's just a simple change in numbers, and we're good to go. So again, how I like to write is I started with x equals 0 and x is equal to the square root of 3. And all I need to do is plug them into u. So if I plug in x here, 0 would give me 0 squared plus 1. That's just going to be u is equal to 1. And when x is equal to root 3, I plug in root 3. Root 3 squared is 3 plus 1 is 4. So I'd get u is equal to 4. So pretty simple change in variables. Actually, makes the numbers easier to work with in this case. And again, I could pull the 1/2 out front. This would leave me with 3/2. Antiderivative, or integral of the square root of u, which I could write as u to the 1/2 with respect to u, from 1 to 4. And now I just have a simple power function. I could use the power rule. So adding 1 would give me 3/2, and I need to drop the reciprocal. I have a 3/2 up front, and this will all be evaluated from 1 to 4. So after solving this antiderivative and dropping the reciprocal, notice that 2/3 and 3/2, well, those are just going to cancel each other out and make 1. So I end up just getting u to the 3/2 evaluated from 4 to 1. So that would give me 4 to the 3/2 minus 1 to the 3/2. And the 3/2 power is the same as the square root cubed. 4 square root is 2 cubed is 8. And 1 to any power is always 1. So here I'm actually just going to get 8 minus 1, or 7. I get a really simple answer because the numbers were chosen well, but what we see is we have some practice using u substitution, and really the key new thing for this video is how do I deal with definite integrals. My recommendation is just change them to u, and you will be covered.